Common element C is focused on representativeness considerations that are common to field measurements and sample collection. As you recall from common element B, data of known quality is delivered to the data user with information on two major aspects. First, how good the data is in terms of accuracy and precision of the measurements or analyses, and second, what the data represents in the environment. As a field operator, you are in charge of assuring and communicating data representativeness, and this element will help you to do that. The first topic is an introduction to the concepts of natural variability and the concept of a sample. The second topic provides ways to enhance the representativeness of samples. Topics 3 and 4 discuss the importance of the where and the when, and show real-life examples of why it matters. A summary of the representativeness element is provided in Topic 5. This element is a continuous lesson, with the first topic setting the stage for the rest. We recommend that you go through the screens in sequence, but you can also click on any individual topic to go to it directly. This topic is an introduction to the concepts of inherent variability and the concept of a sample. Suppose you are monitoring dissolved oxygen in your stream. You calibrated your instrument in the morning to assure the accuracy, which is how close your result is to the true value, but you still need to determine your precision, or how close one measurement is to a repeated measurement. Now, you walk around the stream and take measurements at different places. You discover that you get different results if you move your probe from the riffle to the pool, and you definitely find less dissolved oxygen at the bottom of the pool. Is there something wrong with your probe? Or is this a real representation of a slow-flowing stream with a pool full of organic matter at the end of the summer? How can you separate the inherent variability from the measurement noise or malfunction of your instrument? Well, you have done most of it already when you looked at different locations, characterized the inherent variability, and recorded it. Taking repeated measurements, A with the same instrument, B at the same time, within a minute or two, and C at the same place, to the centimeter or two, will allow you to evaluate the precision of your measurements with this instrument. Very often, particularly in slow-flowing waters, the magnitude of inherent variability far exceeds the imprecision of our instruments. This is why it is so important to select the where and when in a way that will address the monitoring intent. For example, when your intent is to capture the worst-case scenario for cold water fish in terms of the lowest oxygen concentrations, you will go to the creek at dawn at the most critical time of the year, during the hottest part of the summer when the flow discharge is the lowest, and you would target pools where these fish are found. It is also important to record the where and the when in a way that will allow us to communicate what each measurement result actually represents. For example, was it taken at the top or the bottom of the water column? In this scenario, you are collecting samples for nitrate analyses in the laboratory. You are still at your slow-flowing stream with its pools that are full of organic matter, and it is the end of the same summer. The inherent variability in nitrate concentrations can be evaluated if you take discrete samples from different habitats or depths and analyze them separately. Often you will find that it does matter where you collected the sample. Once you take a chunk of water out of a creek, it becomes a sample. The gray zone in the schematic on your screen signifies this special status. An independent sample can be viewed as a unit of representativeness. Anything that happens to the sample later, whether it is split and sent to different labs in order to compare what they find, or the analyst takes 3 replicate test tubes from the same jar, is about the handling and analysis, not about what's happening in the creek. In other words, the lab replicates results, which can only tell you what the repeatability of the measurement system is. It is part of the measurement noise. So, how can you separate the inherent variability from the noise of the sampling and analysis process? Well, you have done most of it already when you collected independent samples at different locations and analyzed them separately, thus characterizing the inherent variability. To evaluate the noise, you must take duplicate samples at the same time, within a minute or two, and the same place, to the centimeter or two, and then run both of them in parallel through the entire shipping and analysis process. These field duplicates, or field dupes, allow you to evaluate the reproducibility of the entire sampling and analysis process. Just to clarify the language, USGS uses the word replicate for what comes out of the same sample jar, versus the word duplicate for another jar taking water that's still in the creek. Replicates show the repeatability of the analytical run, while duplicate samples show the reproducibility of the entire sampling and analysis process. Both are tools for evaluating precision. There are different approaches taken or not taken to separate inherent variability from the noise within our sampling and analysis process. The quiz on your screen asks you the same question you've heard before. How do you separate inherent variability from measurement noise? You are given 5 options. Please take a moment to read them. Sometimes it takes a lot of effort and resources to categorize the inherent variability. You might be asking, why don't we just average it? Well, if you recall the dissolved oxygen scenario 3 screens ago, you will probably come to the conclusion that the average concentration of dissolved oxygen will not really matter to the critters. Mr. Trout might even ask you if you remember the story about the statistician who drowned in a pond that had an average depth of 6 inches. Fortunately, when we use probes to take field measurements of dissolved oxygen, temperature, pH, or conductivity, the level of effort is low enough to permit some spatial characterization. And because the dissolved oxygen concentration at the same spot does change during the day as well, the use of data loggers allows for excellent temporal characterization of the ambient conditions, as you will see later in this element. So we know what to do about field measurements, for example dissolved oxygen, but what about sampling for nitrate analysis? Sampling and analysis cost much more, and getting an average nitrate concentration may work well, particularly when you are looking at total quantities or loads of constituents coming down the pipe. So in this case, it is okay to fold the natural variability into an average. For example, if you average the nitrate concentrations shown earlier, you will get a good idea about how much nitrate is available to the water plants in your creek. Come to think of it, it may be good to combine the samples before doing the analysis and save all of the analytical cost. The next section shows you how to do exactly that. Click on a topic to start, or click the Next button to see them in order. As you recall from the previous section, nitrate concentrations in a slow-flowing, highly enriched creek may be different in different habitats, as signified by the different numbers shown in the picture. Sampling each location and analyzing the samples separately is expensive and may not be necessary. In some cases, you can create a composite sample. A composite sample is made of several subsamples collected at different places or times. Note that a composite is depicted as a large bottle in the gray zone on your schematic to denote that it is fundamentally different from the samples you have seen earlier. The composite is still a unit of representativeness, but it provides a representation of average concentrations without any information on the inherent variability. Compositing is a useful thing to do when we are interested in total quantities or loads of a substance. Like any other sample, a composite sample can be split for analysis at different labs, or divided into aliquots for different purposes. Here is an example of temporal variability. Constituent concentrations may change dramatically in the course of storm runoff flow events. Existing data indicate that the pollutograph, or the plot that shows the concentrations of a potential pollutant, often follows the hydrograph, which is the plot that shows how the water level changes over time. If you want to characterize the temporal variability in concentrations, you will need to collect a number of discrete grab samples during the rising limb of the hydrograph, or when the level in the stream is rising, during peak flows, and during the falling limb of the hydrograph. Then you need to analyze them as discrete samples. If you are short on funds, or interested only in the average pollutant concentration, you can composite all your discrete storm samples and perform fewer analyses. But you will not know how concentrations have changed during the course of the storm. So far, we're talking about collecting many samples in many jars during the storm. Alternatively, you can collect a composite sample directly in the field, taking subsamples at equal time intervals or equal flow intervals into the same big bottle. Stormwater monitoring programs in California often use automatic samplers to collect flow-weighed composite samples. When all compositing is done, the samples are split and dispatched to different labs for different types of analyses. The results of each analysis represent the event mean concentration, which is then used in conjunction with flow discharge volumes to calculate loads. You have seen how compositing several subsamples can enhance the representativeness of a sample. Splitting up a sample into several aliquots that represent the same thing is another challenge, particularly if the sample keeps changing as you homogenize it, as a water sample with suspended solids will do. The user of your data assumes that the aliquots are identical and that the suspended solids are distributed evenly between them. For example, the hardness measured in the aliquot for nutrients and other conventional parameters can be combined with the copper concentrations as analyzed in the aliquot for trace metals for comparison to water quality objectives. Section 4.5.5 in Module 4 shows the churn splitter for aliquoting non-homogeneous water samples. Other ways of aliquoting water include gradual transfer of sample liquids with a pump or a siphon into the aliquot containers. Use the principle of multiple increments. Line up all the aliquot containers and transfer a little bit of water into each one. Then go back for another round of filling. The same incremental transfer principle is also applied when you are splitting a sediment sample, as you can see in a video in Module 5 and in the picture on your screen. Again, jar A and jar B have the same sample ID, and data users assume that the concentration of pesticides in jar A can be used to explain the toxicity found in jar B. You are probably familiar with the way that spatial scales go, from universal to global to continental to regional to landscape to watershed and so on. During reconnaissance, you often study the entire watershed to select appropriate reaches within the stream network. Then you zoom in to a stream channel scale to select your points within the channel. Then you take an even finer look at the water column to decide where to take a measurement or collect a sample. The spatial scales within a watershed are discussed in the first subtopic. The second subtopic discusses representativeness issues that arise when you combine different types of stations in a monitoring effort. During the planning process and the time when you prepare for reconnaissance, you study the entire watershed to select appropriate reaches within the stream network. The criteria that you might use to break the entire stream network into segments may include stream order, slope or gradient, channel type, valley type, soils, vegetation cover, and many other natural factors. Many people try to get a good representation of each major tributary. If they want to compare one tributary to another, they have to select stations at locations that have the same attributes in terms of these criteria, so that the only variable that changes is the tributary itself. If someone wants to compare their station to yours, it helps if you record and communicate clearly what your station represents in terms of stream order, gradient, etc. Another very important attribute to consider is land use. Urban drainage will affect water quality in a profoundly different way than open space drainage. Land use also needs to be considered in station selection and should be clearly communicated as well. Once you decide where you want to sample your individual tributaries or segments, you are ready to take a closer look. If you take a closer look at the water quality conditions within the environment at the stream channel scale, you will find that the inherent variability is more common than you thought. The scheme on the right side of your screen shows features that you probably recognize already. A widening of the channel that allows emergent vegetation to grow, a riffle, a sandbar, and a confluence of two creeks. It also shows man-made features such as a bridge and an outfall. These may alter water quality conditions significantly when it rains. In the picture on the left of your screen, you can see how inputs from a tributary might look at times. Where is the best place to collect a sample from the area drawn on your screen? Suppose you park your car at the only possible place that's safe, and you must always park in a place that's safe. Where's your best access to the water? The swampy area near the parking lot is not representative. Access to the foot of the bridge may be possible, But the eddies and side pools near the pillars are not representative either. You must also stay away from the vicinity of the outfall and downstream of it if there is any flow coming from it. So you are left with what's going on under the bridge, which represents that tributary, and you need to get to the left fork somehow. That might take some weed whacking. Now you will remember why you brought your telescopic pole. Another important thing to remember is that most protocols request that samples be collected at the centroid of the flow. The centroid is the imaginary line that splits the flow going through the channel into two equal parts. One thing that will help you reach the centroid and really improve your representativeness is an extension of your body. Think of a 12-foot pole extended from the bank, or a bucket lowered from a bridge, and you will understand why you had them on your checklist. You will be able to make good use of devices such as a sampling basket, or a pole and clamp, or use a pre-cleaned bucket with a rope, or a beaker on a pole, in most sites you will encounter. Now suppose that you cannot access the main stem for some reason, and you decide to settle with a chunk of water that is accessible. How far can you be from the value that represents the reality of the bulk of the flow? The table on your screen shows actual measurements done in urban streams at the dates and times indicated. In San Mateo Creek at station SMA 020, dissolved oxygen concentrations were more than twice higher in a small backwater pool that was filled with algae than in the main stem, at a point less than 2 meters away. In Wildcat Creek, we found an isolated pool that had about a quarter of the oxygen concentration found in the main stem nearby. Obviously, the backwater pool and side pool do not represent the main flow, but you cannot always see what they represent, especially if the channel is overgrown with vegetation that you cannot remove.
I have a little bit of rays of sun on the back. I hope it's not in the way.
Another crucial item to communicate is the type of water body that your data represent, or the type of station. At times, lake waters will have lots of chlorophyll A, and you cannot compare its concentration to chlorophyll A levels in your stream in a meaningful way because each station represents a different thing. Streams are the kings of suspended sediment, and you cannot compare the turbidity you see in streams with what you see, for example, in the middle of the ocean. So, it does matter what type of station you got that sample in. Click on a topic to start, or click the Next button to see them in order. The flow conditions and time of day in which a measurement was made or a sample was collected often have a very significant influence on the outcome. These plots were taken with a data logger in a slow-flowing river in summer, and they definitely tell you why you need a data logger for this type of job. The diurnal variations in dissolved oxygen spanned amplitudes of more than 8 milligrams per liter, and the pH values ranged between 7.5 and 9.2. Values in these ranges can spell life or death to many critters. The worst-case scenario for dissolved oxygen is at sunrise, around 6 a.m., as shown in the lower arrows, and for pH it is around 3 p.m., as shown in the arrows extended from above. If the intent of your study is to document the worst-case scenario so that we know if the critters will be harmed or not, you would come to do your dissolved oxygen measurements at 6 a.m. and come again to do your pH measurements at 3 p.m. When you deliberately choose the timing to target certain conditions based on your knowledge, you are using the targeted or directed sampling design principle. You have seen a picture of a storm hydrograph in section 2.2 above. What goes in the water during the rising limb of the hydrograph may be totally different from the situation during the falling limb, and both of these conditions are totally separate from dry weather conditions. In fact, water quality data collected during dry weather cannot be mixed with wet weather data in California. So if you take the quiz on your screen, So far, you have seen how the directed or targeted sampling design principle is applied in timing the monitoring activity to capture the worst-case scenario conditions. The same sampling design principle applies to station selection. For example, when we monitor just downstream of an outfall with the intent of evaluating the impact of the discharge, it is deliberate, based on our knowledge, and directed to our intent. As you notice, the sampling design principle is applicable both at the temporal scale, that is, how we choose the time to monitor, and at the spatial scale, that is, how we choose our stations. So far, we have talked about the directed sampling design principle. The schematic on your screen shows other options. For example, if you cannot use continuous monitoring devices with data loggers, and you cannot go to your station at 6 a.m. very often, you might decide to conduct routine monitoring. In this case, try to visit each of your stations at the same time of day on every trip, so that all data points will represent the same diurnal conditions and will provide information about seasonal trends. In this case, you will be using the systematic instead of the directed sampling design principle. If you want to apply the systematic design to your routine monitoring in the same way that others are often using it, then do all your measurements between 9 a.m. and 11 a.m. You will not be capturing the worst-case scenario, but that was not your intent anyway when you chose to do routine monitoring. Alternative approaches use the probability-based sampling design principle, often called random. On the spatial scale, the random sampling design principle is used for station selection by several national and state monitoring efforts in order to get an unbiased picture of the conditions in our waters. On the temporal aspect, folks often use the random design to deliberately show up at unexpected times. For example, when they do their stream watch patrols. If you cannot control the timing of your station visits due to logistical constraints, you will be using a non-deliberate sampling design we often refer to as anecdotal. These are the main points made in this common element. Inherent variability happens, even in fast-flowing rivers, but more so in slow-flowing rivers. Local variation in values is totally separate from imprecision in our measurements, or the irreproducibility of the sampling and analysis processes. It does matter where and when you take your measurements or collect your samples. You can enhance your representativeness by measuring or sampling where the bulk of the water flows. You can average the variable substance concentration values by compositing the samples when it makes sense. You have to schedule your field activities to assure capture of conditions that represent what the study intends to capture, such as the worst-case scenario.